Let's take a look at an example illustrating the Metropolis algorithm. So we're actually going to look at the very first problem that the Metropolis algorithm was demonstrated on. So in the original paper in 1953 by Metropolis, Rosenbluth, Teller, and Teller, this hard disks in a box model was what they demonstrated it on. And here's the model. I'll sort of draw the picture here. And we can think about this model. If I can draw, apparently not very well. So this is a model of particles of molecules of a substance. And so let's draw some molecules in here. Let's make them have a color. So there's these molecules, and each of them is represented by just a circle in this box. And they're called hard disks because they're not allowed to overlap. So this is not permitted. This is an invalid configuration. And all of the disks are the same size. You choose some, some epsilon radius, and they all have that radius. And the box, furthermore, it's typically, well, people use different models, but I think the one that they used, if I remember correctly, is it has periodic boundary conditions, meaning that you can allow for one of these disks to sort of wrap around. So the box sort of wraps around in this way. Or if it was in the corner like this, then it's going to have a little piece in each of these corners. So it could sort of move through here and come back around the other side. That corner looks funny. So topologically, actually, this is topologically a torus. That's not important, though, for you to understand. Okay, so this is sort of the setup, and this is used as a model of a substance, and physicists are very interested in this model because it's a theoretical model for to try to help them understand. I'm not a physicist, so forgive me if I butcher any of the physics here, but it's to understand phase diagrams and the transitions between phases. So if you remember from your chemistry, if you took chemistry, that you have this sort of prototypical phase diagram: solid, liquid, gas. Usually, very often, it looks something sort of like this. And on this axis is temperature, on this axis is pressure, and a subject of great interest to physicists is understanding phase transitions. So when you go from a liquid to a gas, for example, when you boil water, or water, it's you're turning it from a liquid into a gas, or when it goes from water to ice, it's going from a liquid to a solid. And this model was proposed, this hard disks in a box model, or sometimes they generalize it to hard spheres in a box. You make this like a three-dimensional box. And this was proposed as a model a theoretical model to try to understand this very general sort of picture, because so many materials, so many substances have a sort of prototypical phase diagram like this. So they tried to apply so they did apply Markov chain Monte Carlo to simulating this model. And what they were particularly interested in doing in that paper was trying to find, so for what you learn in chemistry, one of the things you learn probably is the ideal gas law, PV equals nRT. And this is the ideal gas law. It doesn't hold in general. And they wanted to try to figure out the corresponding equation of state. This is called an equation of state. They wanted to find the corresponding equation that governed the relationship between these quantities, between pressure, volume, number of particles, and temperature. This is actually moles in this equation, and temperature, and R is just a constant here. And they wanted to find the equation that would govern the interaction of the particles in this theoretical model. And so what they do, the sort of thing that they do is they put a probability distribution on this each of these configurations. So maybe I should say what the configurations are first. Let's say what that is. So we're going to put a probability distribution on all the configurations that this model can take. And each configuration is the following. So X is going to be a configuration, and it will have it tells you the position of all of the particles. So let's say we have capital N particles, and let's say that this is just like a square from 0 to 1 in each of these directions. And since we've only talked about countable or discrete MCMC, let's go ahead and assume that this has some very fine discretization here. Some very fine discretization. So there's only finitely many positions that each particle could take. And the position of a given particle is described by its x-coordinate and its y-coordinate in the box. So in order to describe the configuration of all of the particles together, we need to specify, let's call this the, since I'm using x for something else, let's call this the r coordinate, and let's call this the s coordinate. So we need to specify the r and s for each particle. So we need to have r1, s1, r2, s2, up to r capital N, s capital N. Okay, so that's a configuration. That's a possible state of our system. And let's put the following probability distribution on these. I'm not going to make it precise, but this is the one that they used. So they use, or the general form of probability distribution that they suggested and that they used. And it's a Boltzmann distribution. Boltzmann, named after Ludwig Boltzmann, the Austrian, the father of statistical physics. And he invented, well, he came up with the concept of entropy. Entropy is due to Boltzmann, but he didn't get credit for all his brilliant work in his own lifetime. He was a pariah in some sense. But anyway, so I digress. So back to this is the Boltzmann distribution, which is the classical type of probability distribution that physicists like to put on things. And this E here I put epsilon, that's a different epsilon than this. Maybe I should use, like, I don't know, some radius here. That was the radius. But this is the energy associated with a given configuration. And this T here is the temperature, and K is the Boltzmann constant. So, and Z is just the normalizing constant. So this, we could rewrite this as 1 over Z to put it in the form that we use in the Metropolis algorithm, pi tilde of x. So here, this, by the presumption is that the energy function, whatever it happens to be, is easy to compute. You can just readily, for any configuration x, it's just very simple to compute, and t is something that you fix ahead of time. You choose t, and k is just a known constant. But z is incredibly difficult to compute. It's intractable to compute. Okay, so that's our setup. And so one thing to note here is that when n is large, this is a probability distribution on a very high dimensional space. It's on, you know, R2n. Well, it's not on all of R2n. It's on like some, it's even not on the whole interval here. It's on, you know, all the discretized points here. You know, the product of all these discretized points, you know, all those discretized points to the 2n. Okay, you get the idea. So how are we going to do, what are we going to do for the Metropolis algorithm to simulate this? Well, this is our pi. This is the distribution that we want to compute an expectation with respect to. So they were trying to, in the experiment, they were trying to do something about this equation, and I think what they were doing was they would choose a particular temperature and a particular number of particles, and then, so this would actually be like nkt, where n is the actual number of particles and k is the Boltzmann constant, and rather than number of moles. And then you know the volume ahead of time. I think that's roughly right. And then they would try to estimate the pressure. And so the pressure, I think, if I understand this correctly, the pressure is a function of x, something like that. That might not be completely right, but it was something like that. They had some function that they were trying to estimate the expected value of. So let me just call it f of x, whatever that function is. So we want to estimate this expected value where x is one of these, is a random configuration distributed according to pi. And pi is this Boltzmann distribution. Oh, and I forgot one important thing here. Sorry, Boltzmann, I have to erase you. An important thing, a part of this distribution, is the support. X has to be valid. So we put this indicator function here. It's 1 over ze to the blah times the indicator function that x is valid. So because we want to put 0 probability on configurations that violate this, that have overlapping particles. That's what I mean by valid. Valid just means that there's no two overlapping disks. Okay, so we've got our pi, and now we need to construct. So here's the algorithm here. It's a Metropolis algorithm. We need to choose a proposal distribution, a proposal matrix, and it needs to be symmetric. So what Q should we choose? Let's switch to a different color. So the Q that they choose in the paper is the following. Well, this is not exactly the Q that they choose. This is a slight variation of what they choose. I'm going to vary it slightly so that it fits with this more sort of standard description of the Metropolis algorithm. So the Q that we're going to define is the following. It's very similar to what they use. So we're going to randomly choose one of our n particles uniformly, put a uniform distribution over the particles. We randomly choose a particle. So maybe we choose this one here. And then we have some predefined constant. Let's say it's alpha. And alpha is the half of the width of a box here. So alpha, so this is alpha, this is alpha, and this is alpha. And so then, our first step in a move, a proposal that we would choose would be we randomly, uniformly randomly choose a particle, and then we put a uniform distribution over all of the points in this box. According to this discretization, we have some discretization, and consider all of the possible points in that box. So it's just this very fine grid of points. Put a uniform distribution over those and choose a point uniformly from that. So maybe we choose this point here. So that's our Q. So let's see. So Q, maybe let's say Qx xi. I won't write out the whole thing, but it's 1 over n for the uniformly choosing one of the n particles. And then it's the indicator function that we moved only one particle and that it was in this box. So moved one particle. Maybe I could write it formally, I guess. Let's do that to be clear. So Ri Si equals Ri prime Si prime for all I except for 1. So this is saying that all the particles are in the same positions except for one of them, and let's call that one k for some I which is k. And then for that k we have Rk minus rk prime less or equal to alpha, and hold on, I need to reset my timer. Okay, sk minus sk prime less or equal to alpha. So that's saying, this is the indicator saying that we moved only one particle, and that particle has been moved somewhere within this box. And I'm implicitly assuming that they're, one of these discretized points. And then we have some constant. Let's say we have to have some constant. So we have to divide this by c, and c here is the number of points in this alpha by alpha box. Or it's actually, I guess, 2 alpha by 2 alpha box. This is the number of points according to the discretization that we chose. So this is so the first part is we uniformly choose a particle, and then we uniformly choose a movement of that particle. So in this case, we would have chosen, for this one, it would have been k. We had chosen k, and k, the kth particle, and we moved the kth particle. Okay, so that's our proposal matrix. Hopefully that's clear. That's our proposal matrix, and so that was the first. So here we have chosen a proposal matrix. Oh, and we need it to be symmetric. So let's just verify that. Well, this is clearly symmetric between x and x prime here, and these are symmetric also. That's pretty clear. So this is indeed symmetric. And what's next? So we are doing the Metropolis algorithm. We chose our proposal matrix, and then we initialize. So let's say, it doesn't matter. You just randomly choose some initial distribution, not initial distribution, some initial configuration of these points, as long as it's just some valid configuration. So we do that. Okay, that's our x0. And now we iterate. So for each step in the iteration, we sample from our proposal distribution. We sample, and that's just using that process that I just described. You randomly choose a particle, then uniformly choose a particle, and then if we chose this one, then we uniformly choose a move within this 2 alpha by 2 alpha square, and maybe we chose this point. So that's all the same positions, except this one here is going to be our x that we sampled. And now we need to decide whether we're going to accept or reject that proposal. So how do we do that? Well, we evaluate this. Well, first we sample a uniform 0, 1, and then we evaluate this ratio, pi tilde x over pi tilde xi. So we have pi tilde here. Pi tilde, maybe just to be concrete, let's write what pi tilde of x is. Pi tilde is this e to the minus epsilon x over kt times the indicator that x is valid. So if we happened to, so it could have happened, say there was another guy here. It could have happened that this proposal would result in an invalid configuration, and in that case, this would be 0. Okay, so we evaluate that ratio, and we can just readily do that. It's easy to compute that. And then if u is less than that ratio, then we accept, and otherwise we reject. And if we reject, then we just leave him where he is. So let's draw what might happen. So we uniformly, maybe we choose this guy, and let's say we reject, maybe because we got this point and he overlapped. So then and on the next iteration, we uniformly choose somebody. So maybe we choose this guy, and we look at his box, 2 alpha by 2 alpha box. uniformly choose a point in the box. Maybe we choose that point, and maybe we accept that time because according to our random criterion, we decide, or it tells us to accept. So we move him there. And then we do it again. We randomly choose somebody, and maybe we choose him again for, by some chance. We look at the box around that guy, uniformly choose in the box, and then maybe we reject for whatever reason, and so on. So okay, so I think you're getting the picture, and you just do this. You run this sort of little sort of simulation many times for many iterations for say some little n iterations. That's not this little n. This is the number of moles. The number of iterations. And then that gives you your Markov chain. That gives you this Markov chain right here, x0 up to xn. And this was the problem that they originally described MCMC on. So I think it's really cool that it's such an intuitively understandable problem. You can just visually see it, and you can sort of understand why it makes sense. So the reason why MCMC makes sense on this model is because this indicator function, this validity constraint, makes this a very complicated distribution. And so it's not easy to just integrate over this, with respect to this distribution because of this hard constraint. And furthermore, I mean, your energy function, I haven't specified what it is. That might be some complicated thing too. So there's that, and then not to mention this function f, whatever that happens to be, that might be complicated as well. And yet, with MCMC, what allows you to make it work is that you can move around easily in this space. You can move around once you're in a valid configuration, and it's sort of a high probability configuration. You can get to other high probability configurations easily because they're just nearby. You just move these guys a little, you jiggle these particles a little bit, and you can get to other high probability configurations. And that allows you to sort of explore the space of high probability configurations, and that's what makes MCMC work in this example. Okay, so I hope that was a useful illustration for you to understand, how this algorithm, this Metropolis algorithm, is implemented in a practical problem. Okay, I hope you enjoyed that.